Excellent. I think we can start. We can start again. Welcome back to the fifth and last day of our CosmoLattice school of this year. Thank you guys for connecting. This is the next lecture is actually a practice session. So it is perhaps the last opportunity to ask doubts live about your attempts to run the code, to compile, etc. We can dedicate some time to the actual session itself, no? Where Paco, who is going to take the lead of the session, is going to tell us, is going to show us how to run with gauge fields. But we are happy to take questions from the beginning also, in case you have some doubts accumulated as of now from your previous runs. So please, if you do want to ask something, share something about your output or your experience running CosmoLattice in the previous days, please let us know. And now is a good moment.
Good morning.
Morning.
Good morning.
Okay, let me repeat for those who just joined. In case you have some doubts, this is of the code itself, or how to use it, how to install it, how to compile, how to run it, how to plot things. This would be a good moment to ask things in this practice session. Maybe Paco, we are going to start with your session. You show us how to do gauge fields. And then, well, again, questions about these particular runs or previous ones are welcome. So please
Okay.
go ahead, Paco.
Okay. Okay, so let's start. So today I'm not going to use the slide because the model that I want to show you, it's written in detail in the user manual, in fact, in section 5, which teaches you how to run your first model with gauge fields. All right. So so I guess the font size is large enough. Not I can make it larger. All right. So I think the idea of this session is to show you like the simulation. So how CosmoLattice can simulate the also what is the most generic theory that CosmoLattice can simulate right now, or at least base CosmoLattice, all right? So the most generic theory that it can simulate, it contains 5 kinds of field species. 3 in particular of these 5 species, 3 correspond to scalars and 2 correspond to gauge fields, all right? So in the scalar vector, well, what we can have is a scalar singlet, like this one, which is the ones that you have simulated in previous session. Then you can also incorporate a complex scalar, which I'm going to call curly phi, all right? Let me decrease this. Curly phi, and a complex doublet that we're going to call capital phi, all right? So in terms of components, let me look for the. I'm sorry, because I thought. Yeah, exactly. So right here you have the fields in terms of components. So the complex scalar has 2 components, and the complex doublet has a two component vector with 2 complex numbers, which depends then on for components. All right, and note that we are including a square root of 2 dividing both the composition in components, and also we are dividing here by a square root of 2. So this is important, just to take into account in order to be coherent with when we write the potential. All right, this is regarding the scalar sector. Right, let's go back to section 5, where the action is written, right? And then we are gonna consider two types of like a U1 gauge sector, right? Where F mu nu is the field strength of the U1 sector. This is what I covered in my lecture on Tuesday. And then SU2 sector with field strength E mu nu, all right? Then regarding the interactions between the different fields, what we're gonna have is a potential, which is gonna depend on all the scalar fields, basically all the scalar singlets you can have, and then the norms of both the complex scalar and the SU2 double, right? And then of course we can also include couplings between the complex scalar and the U1 gauge field through the covariant derivative here, right? Which is written like this, right? So the coupling strength is parameterized by both the char Q of A and the coupling strength GA, and then the complex doublet can be coupled to both. Is coupled to both the U1 gauge fields and the U2 gauge field, also through the covariant derivative. All right. So you can see here the covariant derivative for the complex doublet. It's, as I have said, it's coupled to both to the U1 gauge sector and to the SU2 gauge sector. So yeah, this is the most generic theory that you can simulate the CosmoLattice, well, of course, including an arbitrary number of scalar fields like this, but that like the most generic action that you can simulate is this, but including several copies of scalar fields. Okay, but the generalization is immediate, so we are going to just focus on this. You have to you can build you need to build, of course, gauge independent quantities, and in fact, you can build the electric and magnetic field associated to both the U1 sector and the U2 sector. Right? So we have this is the electric and magnetic energy associated to the U1 sector, and this is the electric and magnetic energy associated to the U2 sector, where A is the color index that goes from 1 to 3. Right? Then, of course, in CosmoLattice, we work in program units, and we have already seen how to define these program units, right? We have the usual definitions for program time and program space, and for the field amplitudes, and for program field amplitudes. Note that all the three kinds of scalar fields are normalized by the same quantity, F star, right? So you just need to fix one F star for all scalars. And as we commented in my lecture on Tuesday, the gauge field, the program gauge field, will be normalized by the omega star, which is the same scaling as that appear in the space-time transformations. The reason for this, remember, is because in the link of the gauge fields is basically the exponential of minus a, the time step or the lattice spacing, and the gauge field. So basically, when you transform the gauge field to program variables, this omega star cancels this one. And then we also work with, we can also define program variables associated to the abelian and non-abelian field strength, which are divided by omega star squared. And then we define also program variables associated to the covariant derivatives, which we divide as omega star in an analogous way to the transformation that we will do for space and time. Right? It's the same transformation. And then, as always, we define the program potential as the original potential written in terms of the program variables, and then divided by F star squared, omega star squared. Right? These are the equations of motion that written in program variables, all right, that CosmoLattice solve. Well, these are the equations of motion in the continuum. CosmoLattice, what does is to solve a discretized version of these equations, and we explain how to discretize these equations both in lecture 5 and lecture 7 with Adrian. And yeah, and so these are the field equations. Then you have like in particular, you have the U1 gauge fields are sourced by an abelian current, and the SU2 gauge fields are sourced by this non-abelian current, right? Which depend on this product of complex of the scalar fields. Not in particular, no, that the U1 gauge fields are sourced by both the complex scalars and the SU2 doublet, while the SU2 gauge field.
Sorry, Paco. I mute you by accident. Can you unmute yourself? Sorry, we lost you 30 seconds.
Okay, so you 30 seconds.
Yeah.
Okay. So I don't remember what I was saying 30 seconds ago, but I guess where I was saying that these are the equations of motion that CosmoLattice solve, all right? Not exactly these ones, but but of course a discretized version of them, which we saw how to discretize, no? Which we saw how to do it in both lectures 5 with me and lecture 7 with Adrian. And as I was saying, no, these are written in program variables, and as I was saying, note that the abelian gauge fields are sourced by this current here, which depends on both the complex scalar and the SU2 doublet, right? While the non-abelian gauge fields are sourced by this current here, which depends only on the SU2 doublet, all right? And of course, we can write the energy density in program units, the pressure density in program units, which has contributions from the kinetic gradient in terms of the scalar fields, and both also the electric and magnetic energies of the U1 sector and SU2 sector. Right? And the same goes for the pressure. And we can use these ones to evolve for the scale factor. We can compute the volume average of these quantities, right, and plug this in the Feynman equations to solve for the evolution of the scale factor. So okay, so I haven't explained this. What we are going to consider a particular potential, right? Which is this one, yeah, right? So it's very similar to the cases that we have simulated before. What we're going to have is a complex doublet, all right, which has 4 components, and the 4 components of the doublet are oscillating around the minimum of the potential, right? This complex doublet is going to have a quartic potential like this. Yeah. Okay, the potential is going to go as lambda 5 to the 4, right? And then we are gonna include 2 couplings between the complex doublet and the other 2 scalars we are gonna have, right? The scalar singlet and the complex scalar, all right? And the strength of these interactions is gonna be parameterized by G squared and H squared, which are two different coupling strengths. Now I'll make you a question: why are we writing here lambda 5 to the 4, while before we were writing 1/4 lambda 5 to the 4? When we were simulating a complex scalar singlet. Well, the reason is because, as I shown before, this complex doublet is 1 over square root of 2 and the 4 vector component, right? So basically, if we now write this in terms of components, all the potential terms within terms of components will have this factor 1/4. And this is also like the same. This is also the same reason why we are not including here a factor 1/2 in the interaction, because this one when we write this phi squared in terms of this the complex doublet in terms of components, a 1/2 factor will appear, basically. And this is also the same reason why we are including a 2 here, right? These factors compensate the square roots of 2 that appear in the definition of the complex scalar and SU2 doublet in terms of components. Very well. So, and then of course, remember that even if it's not within the potential, we also have couplings between the oscillating complex doublet, oscillating SU2 doublet, and the gauge field, both abelian gauge fields and non-abelian gauge field. This coupling is through the covariant derivatives. So what we're going to have is an oscillating SU2 doublet that is coupled to all the other scalar fields and also to all gauge fields, right? So this is going to induce a strong resonance, as we shall see, of all fields, right? This is what we're gonna see in the lattice simulation, right? This is what I was saying, right? There is like this covariant term includes a coupling between the CO2 doublets and an abelian gauge field, and also this one between the includes a coupling with the CO2 doublet and the non-abelian gauge field. So Adrian in Wednesday, I think he already discussed about how to implement this model in CosmoLattice. So um, I'm gonna just review very briefly how to do it, but it's very similar to the case of a scalar singlet. And the only difference is that now in the input file, right, you need to pass to the code the initial values, right? Not only of the these are homogeneous components, not only of the scalar singlets, but also of the complex scalars and the SU2 tablet, right? So in this model, the field that is going to be oscillating is initially is the SU2 doublet. So that's why we said we only give a non-zero component to the SU2 doublet, right? This is the initial amplitude of the SU2 doublet at the end of inflation. And just as a comment, no, this is the initial norm, more specifically, this is the initial norm of the SU2 doublet. But of course, we need to distribute this between the 4 components of the SU2 doublet, right? So this is explained here, but basically what we're gonna do is to what we're gonna do is to in this example is to distribute the power of this amplitude in the 4 components in a homogeneous way. So basically, the 4 components will have the same initial amplitude in such a way that when you compute the norm, this is gonna be the initial. This is gonna be the norm. All right. And then in the input file, you also need to pass the charts, the abelian chart. Sorry, the 3 charts, the abelian non-abelian charts, and also the strength. So basically, you need to pass the interaction strength that appear in the covariant derivatives. Yeah, and then in the simulation that we are gonna show, we are gonna define the resonance parameters associated to G and H, right? So basically, we're gonna set G squared over lambda 250 and H squared over lambda 250, right? Let me check 1 second. I think that I don't know if I should go over the entire model because I think Adrian already shown this. So I don't know if I should jump directly to the simulation, to the results of the simulation. I don't know what you think.
I think it doesn't hurt if you go through it a little.
Doesn't hurt. Okay. So I think no. What I'm gonna do, if you don't mind, is so I have. I mean, what I want to do is to show directly the field, the file. All right.
Sounds good.
So yeah. So I have already done a simulation. All right. I know it's here. So, yeah. So basically, this is the. Give me just 1 second. Oops, sorry. Now I know the font size is too small, even for me. So I wanna.
Thanks. Yeah. If you enhance the font there,
Yeah. Now
all of us. Also, yeah. There you go.
do you see it well? Yeah. Okay, great. So yeah, basically the input file. So I have already commented what you need to implement in the input file, right? So there is nothing really to add here. And then regarding the model file, what you need to do is to basically include the field content of your theory, right? This is the first thing you need to do. And we, as I have commenting, we are gonna include one scalar singlet, one complex scalar, one abelian gauge field, one SU2 doublet, one SU2 gauge field, one of it. We're gonna have one of it, right? And then we are gonna have three terms in the potential, right? As I have shown before. And then we are gonna have, in this case, all three different kinds of couplings between the gauge fields and the scalar field, right? Through the covariant derivatives. So when I have a coupling between the abelian gauge fields and the complex scalars, the abelian gauge field to the SU2 doublet and the SU2 and the non-abelian gauge field to the SU2 doublet. All right. So that's why we have these three functions here that that deal with, which are the coupling managers that deal with these couplings. And as we are gonna have these three couplings simultaneously, that's why we have two in the three functions. We could have a model in which one of these couplings does not exist, so we just set it to false, and that's okay. And yeah, and the rest of the structure of the model is very similar. This model, by the way, I haven't mentioned that, but this model and this input file is included in the code, right? When you download it, so you can have a look, right? Yeah, the rest of the model is very similar. The only thing is that exactly what you need, as I was saying, right? You pass in the parameter file the initial norms of the complex scala and SU2 doublet, right? And then you need to, so basically this function, this parser function with these values, right? And then, for example, for the complex scalar, we use this complexify function, right? That creates a complex number with where this is the real part and where this is the imaginary part. So we are dividing by a square root of 2 precisely, right? Because in both cases, right, to have, as I was saying, the same power, the same amplitude to give the same amplitude to the two components, right? Because if we wanted to just give all the amplitude to one component, we will just do this. We will just do this and then put this to 0. All right? That's a possibility. Yeah, in the SU2 doublet, the same is the same idea. The only thing is that we need to create a SU2 doublet, right? So, vector of two components with two complex numbers, no, in each component. So we use this function, make SU2 doublet, right? And this function creates precisely a SU2 doublet in which the norm is equally distributed in the four components. Yeah, and I think the rest, yeah, the only thing now is that you need to, of course, include write explicitly the potential terms and the derivatives of the potential, right? So in this case, we have three potential terms, right? The lambda phi to the 4 and the two interactions, right? And then you need to write all the derivatives, the derivatives of the potential with respect to the three scalar fields, and then the second derivatives, right? So I forgot to mention, right? But of course, I haven't shown the program potential. So basically, the program in what we do is to specify the program variables in the same way as we did with the scalar field case, right? So f star set to the initial amplitude of the SU2 doublet in this case, omega star to the initial frequency of the SU2 doublet, and alpha equals 1 for conformal time. And of course, we can write the program potential from here, which is this term. All right. So yeah, so what I'm writing in the model, these three terms are precisely these three terms in the potential. So I think, do you have any question until now? Because if not, I will just show you the results of a simulation, of this simulation in particular. So perhaps if there is any question about how to implement a model, it would be a good time to make it. Yeah.
let's wait a couple of minutes then to give them margin to think if they want.
Okay, great. Okay. Yeah, I think I have mentioned everything that I wanted to mention. While you think, I will open my mathematical notebook. All right. I think I want to continue. So okay, so as I have said, the code comes with this input file, right? This one in particular, where the simulation is for 128 points, as I mentioned, and I mean you could try to do it in your laptop. What you will see if you try to execute this model, to run this model with these parameters, is that it goes very, 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 very slow, very slow. All right. In fact, so that's the reason why I have not run this simulation in my laptop. What I've done is to run the simulation in a cluster, which I have access to, and it takes, as you will see, it takes the simulation. In my case, I did it for 16 cores, okay, and it took 50,000 seconds, which is approximately 13 hours. 13 hours. And now this is for 16 cores, all right? So if you were to run the model in serial with only one core, the simulation would take 8 days. The simulation that I want to show you, 8 days. It's very surprising because the lattice size is not particularly big. Like we are only having a box with 128 points cubed, right? But you need to take into account that the simulations with gauge fields, and in particular with non-abelian gauge fields, are extremely slow, are very, very slow. There are two reasons for this. The first reason is because of the number of fields that we have, of fields that we are solving in the lattice, right? So when we go to this potential, so I want to make you a question, right? If we write, sorry, we go to the axiom, to this axiom, right? How many fields are we simulating? Just how many independent fields are we simulating? But before, when we were with the scalar, we were on with the scalar model, we were only simulating 2 fields, right? The inflaton and the other field. And if we put this action, we consider this action. Let's count. We have 1 for the scalar singlet, 2 for the complex scalar, that makes 3, 4 components for the SU2 doublet. This it's already 7 components. We have 3 for the abelian gauge field, so this makes 10. And then we have 9 degrees of freedom, 9 components for the non-abelian gauge field, right? So we have 9 plus 4 plus 4, sorry, 9 plus 4 plus 4. This is, sorry, 9 plus 3 plus 3 plus 2 plus 1, so it's 18. Yeah, if I've counted correctly, we are solving for 18 amplitudes. All right, 18 fields. So of course this makes the simulation very slow, right? So 9, yeah, sorry. So 1 second. Yeah. So this is the first reason.
A question, Paco, apparently, from Antonino.
Okay. Sorry.
You mean the total number of degrees of freedom?
Yes, the total number of independent fields that we are simulating in the lattice. So when we simulate the C2 doublet has 4 components, for real scalar fields. Right.
So any 0 component of 4 vector is set to 0.
No, not in this case. Here we have 4. We have, with 4.
In the gauge case, I mean.
Yeah, exactly. Yeah. So we have 3 for abelian gauge fields and 9 for the non-abelian gauge field.
3 times 3, okay. Yes.
This makes 12, then 4, which is 16, 2, which is 18, and 1 is 19. It's 19 fields, not 18.
Okay.
And if we were to simulate the gravitational waves, we will have 6 more, so we will have 25. Yeah, so this makes the simulation very, very slow.
Okay, thank you.
Yeah, you can talk about the degree of freedom if you want, it's just Paco was talking about field amplitudes. But of course, then you have to multiply by 2 the fact that you have also.
Exactly, you are good point. Yeah, of course, you are good point. You need, in fact, have 38 three-dimensional functions, right, in the lattice.
That you have to follow. Yeah.
Yes,
Yeah,
I have another question, because I said in the initialization you always have the Rayleigh distribution for the amplitude. Is this some kind of requirement from something? Because it's not necessary to have delta correlated in momentum space, no? Sufficient to have the random phase.
No, this is so you mean, so I mean, first of all, we implement a Rayleigh distribution for the complex scalars and the C2 doublet, because this is the same as we were doing with the scalar singlet. But it's true that in this case, if we do that and we don't correlate different component the random fluctuations of different components, then the problem that we have is that the Gauss law is not conserved. So that's why we introduce some correlation between the components.
Okay, thank you.
Okay, so yeah, and this is the first reason. The second reason is because when we write the equations of motion, which in terms of kernels, yeah, these are the field equations written as a set of first order differential equations, right? So in particular, computing the kernels for the U1 and especially for the SU2 gauge fields. No, for the U1 gauge fields, it's not super time consuming, but computing this kernel for the SU2 gauge field implies a lot of operations, right? Because this is written in terms of links in terms of plaquettes, links and plaquettes. So you need to compute exponential of a complex number. And I mean, you go to the code and you see how these functions are implemented. You will see that they imply a lot of operations. So the non-abelian gauge fields themselves already, even if you have one non-abelian gauge field only, it will take longer than a scalar field to evolve, right? So yeah, that's why I have done this simulation in the cluster. So I'm gonna show you the results. So it creates a lot of output files, right? And I think the names are self-explanatory.
Paco, sorry, I was just thinking a little bit about the question of Antonino, and if possible,
yes, please.
Make a remark. So what we have implemented is what it comes by default, as we envisage how to imitate or mimic quantum vacuum fluctuations. But of course, remember that this is not rigid. I mean, if you have a situation in which you want to change the initial conditions with a correlator, with, so some functional form that imposes a correlation, this is also doable and possible, okay? You shouldn't take by default necessarily what we have. What we have is something that guarantees for quantum vacuum fluctuations the right amplitudes, and given the phase correlations imposed, then it preserves the Gauss law, okay? But it's just a choice. It's just a choice,
Okay, thank you.
Yeah. So yes. So now I'm gonna show you the results of the simulation. Let me see, perhaps I can increase it. Yeah. So okay, let's go by part. First, I show the scale factor. The scale factor is a linear function that grows with time, a linear function. And remember that this is conformal time, right? So this conformal time, this if the scale factor goes as thin conformal time, this means that we are in a radiation-dominated universe. And so the equation of state evolves as a radiation domination, like radiation dominated. Yeah, this is the identical to the analogous scalar model that you simulated in the first lecture, right? Perhaps I can show, and then something that I want to show you first is how the H2 doublet behaves as a function of time, right? So here I'm showing you the 4 components of the H2 doublet, all right? Conformally rescaled. Okay, so I have multiplied the 4 components by the scale factor, and of course you can see here clearly that they are almost identical. All right? They are almost identical, even after back reaction, even when you are in the nonlinear regime. So it's very interesting. So this shows that if you remember that I'm putting initially the same amplitude to all the 4 components, right? So what this is seeing is that if you put initially the same amplitude to the 4 components, they will oscillate coherently, right? They will coincide during the entire evolution of the system, which I think is the volume average will coincide with the during the entire evolution of the system. So I think this is very interesting. It's like, for example, if we were to have if we just plot 2 components in a phase diagram, the first component in the horizontal axis, the second component in the vertical axis, we would see that the component, like in phase space, the system evolves always or remains always in the diagonal, right? In the diagonal. Even in the nonlinear regime, when we already have fluctuation, which I think is very surprising. When we have fluctuations of the 4 components. These are random in principle, but they compensate in such a way that in the 5-phase diagram, they stay in this diagram. And we can compute also of course, remember these are not really well, I think the most relevant quantity here is precisely this label is not correct. I'm sorry, this is orbital phi. So basically, no, this is the norm of the complex of the U2 doublet. All right. So this is yeah. So of course, basically it's the same as this. I mean, you can obtain it from the individual components, so you can just plot it directly. This is plotted this is printed directly in an output file. Then we can show the energy conservation, right, or the preservation of the first Riemann equation, right, which is the same as in the Scalar-Gauge. You can use this to monitor the accuracy of our simulation. It's not really good. I mean, you can see that even if you can see at the final time, we have violation of more than 1%. This should be around 2%. So it's not very good. I'm kind of pushing a bit the limits of the simulation. But I mean, so if I wanted to, in this case, I would like to confirm that this simulation is accurate by either reducing the time step or perhaps using a higher order evolution algorithm. Okay. More interestingly is the Gauss law, the Gauss constraint, right? We have 2 Gauss constraints, one for the U1 gate sector and another one for the SU2 gate sector, all right? So, and both, I mean, we have made our discretization scheme in CosmoLattice in such a way that this Gauss constraint must be preserved up to machine precision during the entire simulation, all right? If we preserve the Gauss constraint initially, right? This must be preserved during the entire evolution of the system. Up to machine precision. This is not like the energy conservation, where there is always some degree of violation. And here, it's let me just repeat this. Yeah. So here we have, I mean, you don't see it for some reason. It should be. I think they are both superposed. Yeah. So exactly. So here we have the violations for both the A1 and SU2 sectors, right? So I think the label is wrong. Yeah. So basically, you have here two lines. Okay, that two lines. One for the U1 gates, one U1 Gauss law violation, and the other one for the SU2 Gauss law violation. So you can, I mean, here initially it doesn't seem to be preserved to machine precision, because we are in a situation in which we have a homogeneous, very big homogeneous component with fluctuations, right? But then when the system becomes nonlinear, then this is machine precision. We cannot go better than this. All right. All right. So one more. We can show you the evolution of the energy density component. Let me check. No, in fact, no. Danny has pointed me to Skype that, yeah, they are not identical, that I'm just plotting the wrong quantity. Now, I'm sorry. Now, thank you very much, Danny. Now I have to, I have the two Gauss approximations of both Gauss laws. So the blue one is the preservation of the U1 sector. The red one is the one of the U2 sector. All right. Yeah. Thank you. Now, very well. Now we have the energy density component, all right? We have many energy density components. We have 14 energy density components. So this is going to be a bit challenging to plot, right? But I think I've managed to do it in a reasonable way. And this is the initial evolution of the energy component, all right? So we have blue and orange, blue and brown here. So black is the total one, right? The sum of energy components. Blue and orange are the, and just let me just emphasize that these energy components are conformally rescaled. Okay? So that's why the total energy is, in this case, is more or less constant. So yeah, so blue and brown are the kinetic and potential energies of the SU2 doublet, and then we have an exponential growth, an initial exponential growth of all the energies, all the other energies of all the other components, right? This is due to the broad resonance induced by the SU2 doublet. For example, dark green and light green, which it's hard to see, is the scalar singlet. Dark yellow and yellow is the complex scalar. Dark blue and light blue is the so light blue is the gradient energy of the U2 doublet. Red and light red is the electric and magnetic energies of the U1 sector. Purple and light purple are the ones of the electric and magnetic energy of the U2 sector. And then light orange and the interaction, right? So this is there are many lines here. You know, I understand it's very hard to follow, but the idea is that all the energies of all the other fields are growing exponentially during this broad resonance. This is the initial. This is the evolution of the energy component to the entire simulation. And what I think is very interesting in this case is that well after the start of the nonlinear regime, all the energy components, which are not the potential contributions, okay, all the energy components achieve a stationary regime. So I want to see how this stationary regime evolves. So yeah, so this is what I'm showing here. This is the same figure as before, but I'm showing again. I'm sorry, the energy, the legend is not correct. Correctly. Yes. So this is basically the energy ratio associated with component. So basically, with percentage of the total energy, each of the contributions, each of the contributions provide. All right. So in total, these ones, you sum all these lines, these sum 1, all right? And so you can see here very clearly that there is a sizable finite ratio for all these energies, and I just wanted to know how they are distributed in the end, right? In this stationary routine. So this is what I've done. I have extracted the values of the energy ratios, and at the end, they are these ones, right? We have 9% of the final energy is stored in the kinetic and the. So let me emphasize one thing first that I forgot. Note that there is equipartition between the kinetic and gradient component of each sector. All right. So we have basically the same kinetic and gradient energy for the 3 scalar field, and also we have the same electric and magnetic energy in both the U1 sector and the SU2 sector. All right. So here what I'm showing is the sums, the sums of the 2 components of each sector. So basically, here I'm showing, for example, the kinetic and gradient contributions of each of the 3 scalar fields. So I have, for example, 9% of the energy is stored in the scalar singlet, 12% is stored in the complex scalar, 25% is stored in the SU2 doublet, 12% is stored in the U1 electric field, and 41% is stored in the SU2 field, SU2 gauge field. All right. So I think we could make a break because I've been speaking for 45 minutes.
Yes.
And
perfect, Paco.
then I will need just, I think, 10, 15 minutes to finish this, and then we can proceed to answer questions people might have.
Sounds good. Let's take the 5 minutes break first, and we reconvene in 4 or 5 minutes. Okay, thank you.
Right. You're welcome. Do you hear me well?
Yes, Paco, we hear you
Okay.
well. You want to start back?
I wanna drink some water.
Or we wait 1 minute?
Let's wait 1 minute.
Okay. Just go ahead when you feel ready, okay?
Okay. Yeah, I think I'm gonna continue. Okay, so what else? Yeah. One thing that you could also be interested in plotting is the evolution of the equation of state. All right. So the equation of state is just the ratio between the pressure and the energy density. All right. The energy density, of course, is the sum over all components of the energy by definition, and then the pressure is basically the kinetic term, the kinetic scalar terms minus 1/3 of the gradient scalar terms plus 1/3 of the electrical magnetic energy minus the potential terms. Right? This is the pressure definition, as you can see from, for example, in the slide. And yeah, as I was commenting before, if you plot the equation of a state, doing the linear regime is oscillating between 1 and -1 due to the oscillations of the homogeneous component of the SU2 doublet. But then when after the nonlinear regime starts, the equation of a state goes to 1/3, basically, to radiation domination, which is compatible with what we were seeing in the evolution of the scale factor before. Right? In fact, the final value of the equation of the state is almost 0.30. Okay, so and then I think the final thing I want to show in the simulation is the spectra, right? So basically, yeah, you have a spectra field associated to each of the a spectra file, sorry, associated to each of the 5 species that we are simulating. And let's start, right? First, you have the spectrum of the scalar singlet, right? And you can see that it grows during the initial linear regime, and then when the non-linear one starts, it propagates to the ultraviolet, right? Here, the infrared coverage is not very good. So if I wanted to repeat this in order to make a better simulation, I would try to reduce a bit the infrared momentum here. Although there is not a lot of ground to play with, because the problem is that, not in this case, but for other fields, the spectra propagate too much to the ultraviolet. So I would probably need to go to 256 points if we wanted to improve the simulation, which is very time consuming, as we have just discussed. This one is the spectrum of the norm of the complex scalar. So for complex scalars and SU2 doublet, what we plot is the spectrum of the norm of the field, right? So this is the spectrum of the norm of the complex scalar. Please ignore this label because I think the labels are wrong. Okay, I'm sorry. This is the spectrum of the norm of the complex scalar. All right, which behaves in a very similar way than for the scalar singlet. What else? This one is the spectrum of the electric energy of the electric field. This, and then it has the very similar behavior than the other fields, right? It's just you have an initial stage of broad resonance and then a propagation to the UV. And this is the spectrum of the magnetic energy, right? Of the magnetic energy. One thing that I find curious, and I don't know why, is that for some reason the propagation to the ultraviolet for the electrical magnetic field, it's more like it propagates to higher scale in this case than for complex scalars. That's for scalar field, and I don't understand this why is it? So that's why the reason why I was saying that I cannot reduce the ultraviolet cutoff of the lattice too much, because this is already on the limit of what would be acceptable. And of course, you can also plot the spectrum of the electric and magnetic energy associated to the SU2 gauge field. So this is the electric energy of the electric spectrum of the non-abelian sector, and this is the magnetic one. All right. And then you can also plot the spectrum of the norm of the SU2 doublet, which has also a very similar behavior. Yeah, and with this, I have shown you all the results of the simulation. So I think that this will be a nice time to answer questions, if you have any. Or if you want to show anything else of the simulation, that would also be fine.
Yeah, let's take this opportunity now that we have like a half an hour slot. If anybody wants to ask something about their experience running the code, let it be doubts, complaints, or highlights.
Complaints also?
Well, let it be whatever, you know. Demands.
So there is one question in the chat. Ah, no, sorry, it's just a message. Okay.
Let's stay here for a while. If it turns out that there are no questions at the end, we can always cut this first session, and then we reconvene in half an hour earlier than scheduled, you know, because actually our next lecturers, one of them is in Korea, and I think he would appreciate it. Well, good. I think if there are no questions, then maybe we can cut it here.
So at which time do we reconvene?
Let me first ask, is there anybody who would like explicitly that we stay here so we can take care of some doubt? Please say, speak out loud. Okay, otherwise, I think, well, for us it's 10:04. So what about reconvening at 10:30 in 25 minutes? Okay, so we take a coffee break now and we come back half an hour before schedule. Somebody gave an okay there, but I cannot really see who. Yeah. Oh, the lecturer. Okay, cool. Guys, so we'll see you at 10:30 European time. Let me see if I do that right. That should be what time in India? 2 p.m. I believe, and 4:30 in China. I hope I got it right.
If not, just take your time at some 25 minutes.
If not, put 25 minutes in the clock right now. Okay, guys, see you then in 25 minutes. Thank you very much, Paco.
See you.
You
Thank
all.
you.